America's Big Boy is celebrated as the world's largest steam locomotive, but a forgotten Soviet giant was actually bigger and more powerful. That surprising fact that a largely unknown Soviet locomotive surpassed Big Boy in both size and theoretical power is the hook of this story. The Soviet AA-20 stands alone in railway history, a locomotive so rare that even in Russia few have seen more than a faded photograph or a cryptic line in a registry. Its name carries a logic rooted in politics and engineering. The double A for Andrei Andreev, the powerful Soviet official who championed its creation, and 20 for the strict 20-ton axle load it was built to obey. Unlike the mass-produced American giants, only one AA-20 was ever finished. The story begins not in the Soviet Union, but in the workshops of Krupp in Germany, where the massive steel frames were forged and assembled before being shipped east. Final assembly and modification took place at the Voroshilov locomotive factory in Ukraine, where Soviet engineers adapted the design to the realities of Russian railways. Completed in late 1934, the AA-20 was a prototype by definition and by fate. No sister engines followed. The locomotive's sheer size and unconventional 4-14-4 wheel arrangement broke records. But it also created a paradox. A machine built to be the pride of Soviet industry, yet so rare that its existence is almost a rumor. Official archives offer only scattered traces. No full set of blueprints, no detailed test logs, not even a surviving bolt. Most of what remains are fragments, a handful of black and white images, technical summaries, and the recollections of a few railway workers inside the Russian Railway Museum. A curator holds a brittle ledger, its pages filled with handwritten entries from the 1930s. He points to the AA-20's number, confirming that only one was ever built, and that its operational life was brief. The scarcity of records is as much a part of the AA-20's story as its engineering. In a country that built thousands of locomotives, the AA-20's shadow lingers because of what it tried and failed to become. Its existence is not erased, but preserved in the margins, waiting to be pieced together from the few documents and memories that survived. In Stalin's Soviet Union, railways became more than a means of transport. They were a symbol of national might. The first 5-year plan demanded miracles from the country's engineers, new mines, new factories, and above all, new ways to move mountains of coal and steel from Siberia to the west. Every ton of freight counted, and every kilometer of track carried the weight of political expectation. Soviet planners, working under the gaze of government directives, were told to set records, not just meet needs. The AA-20 was born from this climate of ambition. It was not enough for Soviet locomotives to match their Western counterparts. They had to surpass them in scale and spectacle. The government's push for headline-grabbing projects meant that factories and design bureaus scrambled to propose ever larger machines. The AA-20's 14 driving wheels, its 33 meters in length, and its massive firebox were all deliberate choices. Features meant to impress not just railway workers, but international observers and party officials. Official bulletins described these machines as proof that socialism could outbuild capitalism. In propaganda posters, locomotives thundered across the steppe, trailing banners that promised abundance and progress. Beneath the surface, the pressure on engineers was relentless. Every design decision was scrutinized for its potential to break records. The 20-ton axle load, for example, was not just a technical constraint, it was a number that appeared in reports to the Central Committee, a target that signaled Soviet ingenuity could conquer the limitations of existing track. The AA-20's very name, honoring Andrei Andreev, tied its success to the reputation of a rising political figure. Failure was not just a technical setback. It risked undermining the image of Soviet progress at a time when every achievement was measured in global headlines. In this world, a locomotive was never just a machine. It was a statement, and sometimes a gamble. On paper, the AA-20 stands as a monument to extremes. Its overall length stretched to 33.73 meters, over 110 feet from buffer to buffer, making it the longest single-frame steam locomotive ever built. 14 driving wheels, arranged across 7 axles, dominated the center of the machine. Their solid steel forms meant to distribute the engine's enormous weight evenly across the rails. Each axle carried a strict 20-ton load, a number chosen to match the limitations of Soviet track while still maximizing the locomotive's pulling power. The firebox alone covered 12 square meters, a vast grate area designed to burn the low-grade coal available in the Soviet Union. This immense furnace fed a boiler intended to generate enough steam for a theoretical tractive effort of around 408 kilonewtons. In comparison, the American Union Pacific Big Boy, famous for its own size, carried 8 driving wheels per engine unit and measured just over 40 meters in total, including its tender. Yet in terms of rigid wheelbase and single-frame length, the AA-20 outstretched even this icon. The AA-20's sheer bulk was not limited to its length or wheel count. The locomotive's total weight approached 140 tons, with every design decision focused on maximizing force within the 20-ton axle limit. The massive connecting rods, the oversized cylinders measuring 740 millimeters in diameter, and the broad radial boiler all served a single purpose: to turn as much of the engine's weight as possible into forward motion. No other locomotive matched its combination of length, number of drivers, and axle loading on a single rigid frame. The AA-20 was not just another big engine, it was the most ambitious attempt to turn raw numbers into practical power, a machine built to outclass every rival on paper. In the end, its dimensions became both its claim to fame and the root of its troubles. Soviet planners faced a simple equation: how to move more freight using the rails and resources already in place. The answer on paper came down to weight and numbers. By spreading the AA-20's 140-ton mass across 7 driving axles, engineers could keep each axle's load to 20 tons, the strict upper limit for Soviet track at the time. This calculation promised a leap in hauling capacity without the enormous expense of rebuilding thousands of kilometers of railway. Instead of shorter, lighter trains running more often, the AA-20 offered a way to pull longer, heavier consists with a single engine, maximizing the use of existing infrastructure. Fuel economics played a central role in every design meeting. Soviet coal was cheap, but it was also low-grade, high in ash, low in energy, and abundant in the Donbass and Kuzbass basins. The AA-20's massive 12-square-meter firebox was tailored to burn this poor-quality fuel efficiently. A larger grate meant the engine could use the cheapest coal available, reducing costs for every ton hauled. On paper, this made the locomotive not just a record breaker, but a potential savior for the country's freight budget. The expectation was clear: a bigger engine burning cheaper coal could move more cargo for less money. By keeping the axle load within established limits, the AA-20 sidestepped the need for new bridges, heavier rails, or reinforced ties. This was a major selling point for operations economists who were under pressure to deliver results without ballooning state investment. The rigid frame, with its 7 coupled axles, was seen as a cost-effective alternative to more complex articulated designs. Every calculation pointed to a locomotive that could haul more than its rivals while keeping maintenance and infrastructure spending in check. Freight haul projections from the early 1930s showed a sharp rise in demand along the Moscow-Donbass corridor. The AA-20 was designed to answer that need, promising to shift more coal, steel, and grain than any engine before it. Theory was elegant: distribute weight, burn cheap fuel, and move mountains with a single machine. Yet behind these numbers, the the stresses and strains of such a design waited to reveal themselves. Inside the Voroshilovgrad shops, the AA-20's mechanical complexity became immediately apparent. 7 coupled driving axles demanded an unbroken chain of steel rods, stretching more than 10 meters from end to end. Each joint and pin had to transmit immense torque from the pistons to the rails. Maintenance logs from 1935 show a pattern. Crews flagged accelerated wear on the coupling rod bearings, noting heat discoloration and metal shavings after only a few weeks in service. The rods themselves, oversized by necessity, flexed visibly under load, especially at startup when the full force of the 740mm cylinders acted through the entire linkage. A mechanical specialist reviewing a surviving sketch points to the stress points, where the rods changed direction to follow the uneven vertical movement of the wheels. Each axle, especially those near the center, moved out of alignment on the slightest track dip or curve. The flangeless middle drivers, intended to help the locomotive negotiate bends, only added to the problem. With so many moving parts, even a minor misalignment caused the rods to bind or twist, amplifying forces at the rod pins and bearings beyond what 1930s metallurgy could reliably withstand. Service sheets from the Voroshilovgrad factory detail repeated breakdowns, seized bearings, cracked rod ends, and occasional failures of the universal joints added to allow for curve negotiation. Lubrication routines became frantic. Oilers struggled to keep up with the heat generated by friction, especially on long hauls. Engineers adapted by machining replacement pins and bushings in-house, but the pace of wear outstripped their efforts. The design's logic, spreading weight across more wheels to protect the rails, meant every component downstream had to absorb the resulting forces. The AA-20's rods and bearings became the weak link, vulnerable to fatigue that no amount of maintenance could erase. Even before the locomotive's weight began to deform the track, its internal anatomy was showing signs of strain that would soon have consequences far beyond the workshop. Test runs placed the AA-20 on tracks never designed for such a force of nature. Within weeks, maintenance crews logged a string of rail defects along the test route. The locomotive's 140-ton weight, spread across its 7 driving axles, was supposed to protect the rails by keeping each axle within the 20-ton limit. In practice, the rigid frame transferred every jolt and twist directly into the track. On straight sections, rails bowed outward under the strain. On curves, the effect grew worse. Turnouts failed as the AA-20's wheelbase forced the rails apart, sometimes splitting wooden ties and bending steel plates. Switches designed for standard freight engines buckled under the pressure. Track inspectors reported visible gauge widening after each passage, forcing emergency repairs and, in some cases, temporary line closures. Logbooks from the Voroshilovgrad test team show a pattern of chronic downtime. The AA-20's massive boiler, built for low-grade Soviet coal, struggled to maintain steam on cold mornings. Firemen shoveled furiously, but the grate area was simply too large for the fuel quality. Boiler pressure dropped below safe limits, stalling the engine mid-run. Even when steam held, the couplers, standard Soviet issue, could not withstand the tractive effort. Several snapped outright during test hauls, scattering freight cars and leaving crews stranded in remote sidings. A track specialist reviewing the original field reports notes that the AA-20's rigid wheelbase left no margin for error. On tightly curved sections, the flangeless middle drivers and lateral play at the front and rear axles could not compensate for the engine's length. The result was a locomotive that derailed with alarming frequency, sometimes at speeds below 20 kilometers per hour. Each incident meant hours of recovery, more damage to the rails, and fresh warnings from line supervisors. Maintenance teams, already stretched thin, faced a machine that demanded constant attention but delivered little in return. The promise of moving more freight for less was undone by a simple fact. The AA-20 was too much for the rails it was meant to conquer. Withdrawal from service came not with ceremony, but with a simple administrative order. After a handful of troubled test runs and mounting evidence that the AA-20 could not be trusted on regular rails, Soviet railway officials issued instructions to remove the locomotive from operation. The prototype was quietly moved to the Sherbinka test facility outside Moscow. There, it sat in storage, its massive frame gathering dust while newer, more practical engines took over the country's freight lines. No further runs were scheduled. The AA-20 never returned to the main line, and no effort was made to adapt or improve its design. For a quarter of a century, it remained at Sherbinka, part relic, part cautionary tale, until, in 1960, it was finally scrapped. Not a single part was preserved for display or study. The withdrawal was final, closing the chapter on an experiment that had once promised to redefine Soviet railroading. Union Pacific's Big Boy was engineered with a different philosophy, one grounded in the realities of American railroading. Its articulated 4884 design allowed the locomotive to pivot through curves, splitting the driving wheels between two engine units connected by a hinge. This flexibility meant Big Boy could handle the sharp bends and undulating grades of the western United States without straining the rails or itself. Maintenance crews found the locomotive's standardized parts and proven systems familiar and manageable, reducing downtime and repair costs. Heavy American rails, built to withstand higher axle loads, provided a solid foundation for Big Boy's 32-ton axles and immense weight. As a result, the locomotive hauled 3,600-ton freight trains across the Wasatch Mountains with a reliability that became legendary. A curator standing beside Big Boy's towering wheels points out the practical wisdom behind its success. By balancing size with articulation and infrastructure compatibility, Union Pacific created a machine that delivered power without overwhelming the system that supported it. Gigantism was not just a technical pursuit in Stalin's Soviet Union. It was an ideological one. Record-setting projects like the AA-20 were driven by a culture that valued spectacle as much as utility. Party officials and industrial planners measured success not only in tons hauled or kilometers covered, but in the ability to claim the world's longest, heaviest, or most powerful machine. In this atmosphere, engineering became a means of projecting national strength, and the AA-20's unprecedented scale fit the script. Historians point out that prestige incentives often pulled designers away from practical solutions, rewarding the symbolic over the sustainable. The AA-20's massive frame and 14 driving wheels were as much a statement as a solution, meant to impress foreign observers and inspire the Soviet public. While American railroads built icons like Big Boy to solve specific operational challenges, the AA-20 was conceived first as a demonstration of what could be built, and only second as a tool for everyday work. The question lingers. When a machine is remembered more for its ambition than its achievements, does it become a legend? Or does it simply fade into the background noise of forgotten experiments? Today, the AA-20 survives only in blueprints and black and white photos, a reminder that ambition alone does not guarantee a legacy. As technological icons are shaped by what endures, not just what impresses, history quietly leaves its boldest experiments behind. The real test is not size or power, but lasting impact. What we remember and what we forget still defines the stories we tell. Share your thoughts on Forgotten Giants below.